So we have a set gamma, which is a complete, consistent, and saturated set of formulas. So complete means that it is opinionated. It says at least take any formula. It either proves that formula or the negation of that formula or both. It's consistent, meaning that it never proves both a formula and its negation. And saturated means whenever it proves an existential statement, it does have a closed term. Sorry, it does have a name, like a constant, which picks out the object which is being claimed to exist with some property. Okay, so that's the set of formulas, and maybe I'll state the claim here. Oh no, the claim involves an interpretation. And so let me describe that interpretation. So I is an interpretation which is derived from gamma. So I can put some gamma notation in the name of I, but I won't. And here are the details of it. Its domain is called I subscript D. It's the set of all equivalence classes of closed terms. So that's just a formula, a term that doesn't involve any variables. So it's just function symbols applied to constants, or applied to function symbols, applied to function symbols, applied to constants, and so on. And what is the equivalence class of a closed term T? It's the set of all terms, closed terms S, such that gamma proves the statement S equals T. So that's our domain of objects are all of these things. And we interpreted the function symbols in such a way that if you take any, or when you apply them to an n-place function symbol f to n objects, which are all equivalence classes of closed terms, that ends up being equal to this equivalence class of closed terms. And I've justified that such a function exists uniquely with this property. I should add for closed terms Ti. So you can pick any sequence of closed terms T1 up to Tn, and if you apply the interpretation of the function symbol f to the equivalence classes of those closed terms, you end up with exactly this equivalence class of closed terms. You might like I've got a particular representative here. If you picked different TIs, you might choose a different representative by which to name this equivalence class, but it'll be the exact same equivalence class. And finally, I interpreted the relation symbols, which just say what's true about objects, such that, again, if you take any equivalence classes of closed terms and apply this, the interpretation of this relation symbol to them, that is true or is equal to 1 if and only if this formula is in the set gamma. I could also say it's equal to It's sorry that gamma proves that statement because um, the lemma I proved last week showed that this is equivalent to gamma proves that formula. Um, but like I just defined it this way because it's clear that this elementhood relation is either true or false. But the coherence of this as a definition for when this is equal to 1 is sort of uh, is only well defined as long as I have gamma as a complete consistent set. So which it is, but just for the safety of this definition, I'm just defining it in terms of the elementhood of this formula in this set of formulas. But it's the same as provability. Um, yeah, and again, this is for any closed terms Ti. And I claimed and proved last week that such an interpretation of R exists and is unique with this property about when you apply it to this situation of these closed terms. Um, so just to point out something, like uh, if I want to apply I of R to uh, just some sort of anonymous equivalence class, um, I'm not really sure what to do. Like if I don't if just sort of defining it as an object, um, yeah, it's sorry to know whether or not I of R is true of this collection of this sequence of objects. I need to be able to extract some representative closed term from this equivalence class. Um, and I'll be making use of that too in the proof of the proposition, which I'll state now. So the here's the proposition. Um, it's that this interpretation makes phi true for every phi in gamma. And this is sort of this is the main thing I need to prove in order to say that this will link back to completeness because this I need an interpretation that makes all of the formulas in gamma true. So let me go ahead and begin that proof, and I'll be making use of a lemma, a multi-part lemma that I proved last week. But instead of writing out writing out that whole lemma again, I will sort of reference what property or what piece of that lemma I'm using as I go. So I'll move on to the second board for now. Okay, so here's the proof. So I'm doing this. We proceed by induction on the complexity of phi. And so you could define this like structurally in terms of like directly based on the connectives used or the quantifiers used, or you could sort of count the number of connectives and quantifiers used in a formula and do induction on the number of those things. So then that's just regular mathematical induction. Either one works. I'll just give you the necessary pieces that you need to piece together both of those arguments. So we start with the base case. suppose phi is, I won't do it like that. Instead of mentioning phi, I'll just say, suppose we have an atomic formula, so R of T1 to Tn in gamma. And I'm just remembering I need to add. Okay, so what I'm going to do, actually, this is in two parts. Um, actually, I'll modify the proposition. This is, I'll just call this proposition 1. And I'll modify it to say for every closed phi in gamma. And then proposition 2 will just be the statement without that provision. And I'll show you how to extend it. So for now, all of our formulas that we're talking about, that we're doing induction on, are just all closed formulas. So our base case is when we have some closed formula, a closed atomic formula, which is just a relation symbol applied to some terms. And so I start with it being one of the formulas in gamma. And the first part 0 of the lemma was showing that this was equivalent to the statement that gamma proves R of T1 up to Tn. So it's in the set, so I can prove it from the set, and that's like the proof of that is just you just use the trivial natural deduction proof, which has this formula as the sole premise and conclusion. Okay, so now I know that I of R of these equivalence classes is equal to 1. And this is this point of the recap. This is just essentially by my definition, which showed that this property holds. Because I have this formula R of T1 up to Tn is in gamma, so this has to be equal to 1. All right, now what I want to show is that I makes R of T1 up to Tn true, which is not quite the same as this, but I'll show its equivalent. So what I need first is that just this observation that you take, so let V be any valuation. And to show that, to show exactly that I makes that formula true, what I need to do is show that I, with any valuation of that formula, is equal to 1. And yeah, you shouldn't expect, or you should expect this to be true because there's no, there are no variables in here, so that this valuation should have no effect, and that will be the case. So let me show that now. So let V be any valuation, and now observe that the interpretation with valuation V of the term Ti has to be equal to the equivalence class of the term Ti. And this is straightforward if ti is an inductive argument in itself. So I'll just give you an example um, of why this is true. So I'll do it in red over here. Let me just take some complicated formula. Sorry, not formula, a term like f of g of a. And so if I interpret that term to get some object with this valuation, this is equal to, well, the semantics say I have to interpret the function symbol f and apply that resulting function to uh, the interpretation with valuation v of the argument. So I've moved one step in, and now I just need to apply the semantics again to interpret this. So I interpret g as a function and apply it to the object that the argument picks out. I got the right number of brackets there. And you'll notice that the inner I of v of a is just a constant. It is just the equivalence class of a. And now I'm just noticing that this definition here, I think I sort of claimed that I defined it to be this way for any closed terms ti. I'm wondering if I only sort of achieved that for constants, in which case this inductive argument sort of completes the picture there, or if I did actually show it for all closed terms ti, no matter how complicated. Either way, we know this to be true. So if this definition like this definition involves proving, like, claiming, yeah, yeah, and yeah, and whether or not that I was sort of claiming that for any closed terms of any complexity or just for like constants, I'm not sure what the content of my proof was. Um, but if it was just constants, then it extends as such to any closed terms uh, by this reasoning. Which, if I continue, if I apply I of g to this, then I get the equivalence class of g of a. And if I apply the interpretation of f to that equivalence class, I get the equivalence class of f of g of a. So that complex term. So that's going from here to here. And so I can do that with any closed term, no matter how complicated. So this holds. So now I can continue. Okay. So I of v of t1 up to tn. The semantics, the rules of the semantics say that you interpret the relation R as some relation that holds of certain sequences of objects, and you apply it to the objects picked out by the terms in the sequence. And those objects picked out are, by definition, I of v of t1 to I v of tn. And I just showed that that's equal to this. just so closed terms are interpreted as equivalence classes of those closed terms, and I know this to be equal to 1 by definition, by the way that I defined uh, the interpretation of R, because this formula is in the set of formulas. So this interpretation has to make it true, and that's true irrespective of what valuation you use. So that lets me conclude this. So that's the base case. Any questions about that? Okay. So the next step is we have to consider. Well, I guess there's really two base cases because our system has equality baked in. So an atomic formula is really either a relation symbol applied to some terms, or it's an equality of two terms. You could think of equality as just a two-place relation. But let's just consider this case. So in this case, phi is now an equality of any two terms. So if you've got that statement of equality, that formula is in the set of formulas gamma. Then because S equals T is closed, that can only happen if both S and T are closed as terms. So from that fact, I know that, well, if I take any valuation V, so let's say let V be any valuation, which just assigns objects to variables, so it won't be relevant. I of V of S is going to be the equivalent class of S, and I of V of T, just the equivalent class of T. But I claim that S and, well, let me just say it like this. I claim S is T. These are the same set of formulas. Because gamma proves S equals T. So I can kind of just appeal to this is the relation I was using to define these equivalence classes. So this is just true for any equivalence classes you form. If some relation holds between two things, then if you take the classes of which those things are representatives, so these two things, then they have to be the same thing. That's just a property of equivalence relations. I could sort of also do it directly by taking any term in this set. So that will be some term u where gamma proves u equals s, and then I could show that u is also in this set by showing gamma proves u equals t, and that would just be a matter of applying this equality elimination rule to interchange the s here with the t. So I could actually derive I could rederive a proof of showing that if you have something in here, then you've got that. If you have a term in this equivalence class, then it's also in this equivalence class, and vice versa. Okay, So then by definition, this makes I of v of s equals t equal to 1. Because the definition of that is that uh, the interpretation of this object and, sorry, of this term and this term are the same object. And that's exactly what I've just shown. So therefore, s equals t is true in this interpretation because it works for any valuation. So that's the second base case done, and now we can move on to a more complex case. So if phi and psi in gamma is closed, then phi is closed and psi is closed. And this is now, what number is this? This is Lemma by Lemma part 2. We have gamma is in the set, sorry, phi is in the set gamma, and so is psi. And if you're wondering what this lemma was, it was just that this is equivalent to this. Was just that, yeah, if I have a conjunction in the set, then I also have the two conjuncts for the set gamma, and also vice versa. If I have the two conjuncts in gamma, then I also have their conjunction is also in gamma. And that that's only true because gamma is complete and consistent. Otherwise, this wouldn't hold. So those were the premises of that lemma. So then I sort of I'm missing a sort of I should have said suppose suppose the claim is true for any formulas with n many quantifiers or connectives. And now I'm showing for the n+1 case. And this is where I invoke the inductive hypothesis on these two formulas. So by the inductive hypothesis, which I stated aloud, I makes phi true and I makes psi true. So by the semantics, I makes phi and psi true. I can sort of unpack that and sort of like the semantics doesn't really get you directly from these two statements to this one. You need to go via the valuation. But there won't be any that'll be completely straightforward. And I think it's just clearer to just state that this follows directly from these two statements by the semantics. And I would just argue that it follows similarly for the negation case, the disjunction case, and the implication case. This just involves, again, applying the relevant statement from the lemma I was alluding to from last week, and then applying the inductive hypothesis to those pieces. to regain the statement that you want, that the complex formula is true in the interpretation. So I won't go through each of those, but they make use of that lemma, of each of the different parts of that lemma respectively. And so I'm not going to do those to make room for the more interesting quantifier cases. So now I'm going to erase the recap board and pray that I don't get kicked. Seems to be working smoothly. Okay, so now I'm at the case where if exists x phi is in gamma, and is closed, by all right. So the definition of let me just inspect the free variables of this formula. So the free variables of exists x phi is the empty set. That's exactly what it means for that formula to be closed. And by definition of how we define free variables, phi without the variable x has to be empty. So if you take the free variables of phi and you remove x, then you should still have the empty set. So x may or may not be in this set. But I know that this set difference has to be empty. Okay, now with that reflection, I'm going to use the fact that gamma is saturated. So since gamma is saturated, the exact nature of being saturated is that if I have an existential statement, then there is some witnessing constant for it. So I know that phi you want me to write in a certain spot. Phi of c for x is in gamma for some constant c. That's exactly secured by the property of gamma being saturated. But then we notice that phi c for x is closed exactly because the free variables of phi c for x is equal to the free variables of phi without x, because I've substituted it for a constant. So if x was free in phi, it's no longer free in this formula. And no more variables are introduced because this is just a constant. C is just a constant. But I know that this is an empty set. So that's exactly what it means for phi c for x to be closed. So I can apply the inductive hypothesis to phi c for x. So phi c for x is true in the interpretation I. And so now I just need to use these facts to show that I want to show that we show that I makes phi, exists x phi true. And so I need to just pick an evaluation, and show it's true in that valuation. Let V be any valuation, then let me just look at my notes for a second. We claim that IV of exists X y is equal to 1. And to the at this point, we look at the semantics, which says, when does an interpretation with evaluation make an existential statement true? Well, what you need is you need there to be some object such that when you apply the altered version of V, where it sends X to that particular object of choice, that makes phi true. So that's what that's the conditions under which the semantics makes this formula true with this interpretation and valuation. And so I just need to pick some particular object D so that this works. So let me do that now. Consider V prime, which is just V where X is altered to be sent to the object picked out by C. So C is some constant. And so the interpretation of that constant is going to be some equivalence class of terms. And we actually know what that equivalence class is going to be. It'll be the set of all terms provably equal to C. Just give me a moment. Okay. Now I claim that I of V prime of phi is the same as I of V prime of phi with C for X. And this is a trick I've used many times where I have a valuation which sends a variable X to some object, and I just change the formula so that the variable gets substituted for a term which will get interpreted as that object. So that's the reason why I claim these things are the same. And this should be equal to 1. Let me just read why. Yeah, okay, this is equal to 1 because we know, because I makes phi with C for X true by the inductive hypothesis. And the inductive hypothesis applied because, oh yeah, I stated it here. Yeah, it's closed. So I makes phi of C for X true. And making this statement is just that if you pick any valuation, for example, V prime, and you interpret that formula, you'll get 1, which is exactly what I claimed to happen. But yeah, but the truth value of this is the same as this. And so I just exhibited an alteration you can make to this valuation such that it picks out an object for the variable x, which makes the formula phi true. And that's exactly the conditions under which this is the case. Where, yeah, so the interpretation with the valuation makes that existential statement true. And that's exactly what I needed for this. That the statement that it's true irrespective of any valuation. So that's the existential case. I'll finish off with the universal case, and then we can extend it to not just closed formulas, any formula in the set gamma. So I'll do this one a bit quicker. If for all x, phi is in gamma, then phi with t for x is in gamma for every closed term t. And this was exactly the corresponding part of the lemma that I proved yesterday, was that that you can interchange these two things. So by the inductive hypothesis, we have I makes phi of t for x true. For any closed t. And now let v be any evaluation. We claim that interpretation with that valuation of for all x, phi is equal to 1. And so to do that, I need to do the same sort of thing as with the existential, but I need to show that if you pick any any modification of this valuation that sends x to any particular object in the domain, then if that altered valuation was v prime, then this will be true. So let's do that. So let d be any object of the domain. So it's some equivalent class of closed terms. And consider v prime, which is the same valuation as v, except it sends x to that object d. Now, for any closed term in the set D, the D is some set of closed terms, we have I of V of T equals D. Whoops. Is equal to the equivalence class of T, which is exactly the set D. And actually, well, this is, I should probably state that about V prime, not V. So now from that fact, I can get I V prime of phi. The truth value of that is the same truth value as I V prime of phi, where I replace t for x, the same trick as before. But this is equal to 1 for exactly this reason here. So hence IV of for all x phi is equal to 1, because if I pick any modification of v sending x to any object, I know that it's going to end up with the truth value of 1. So that's exactly the conditions under which I can make a universal claim about phi over all objects that x could be. So I makes for all x phi true. So that's the universal case. And oh, actually, there's one more case that you might have forgot about, or I guess I forgot about. Uh, Here's the case and proof. We do not have Folsom in gamma, since gamma is consistent. So that suffices to say that if Folsom is in gamma, then then the interpretation makes Folsom true. But it's not the case that Folsom is in gamma, so that's trivially the case. Is that the case that you had in mind? Okay. All right. Let me finish uh, with doing away with this constraint to just closed formulas. So let me put a victorious square in the bottom left of that last board. So I just proved proposition 1, and now I'm going to state and prove proposition 2. Proposition 2 is that if phi is in gamma, then I makes phi true. So this doesn't have the provision of being closed. And here's the proof. We proceed by induction on the size of the set of free variables of phi. Okay. So base case, if free variables of phi is the empty set, this follows from proposition 1, which is just that that I makes phi true if phi is closed, and it is closed, because the set of free variables is empty. Right now, suppose I makes phi true for any phi in gamma, such that the free variables of phi size of that set is equal to n, and let psi in gamma be such that the size of its free variables, the size of the set of its free variables, is equal to n plus 1. All right. Let V be any valuation. So we're going to show that psi is true in the interpretation with the valuation V. and here's how it would do it. And pick some x in the set of free variables. Okay, now think about v of x. This is some object in the domain. So it's some equivalence class of closed terms. So now with classical magic, pick some t in that set of closed terms. Then IV of t is equal to the set of equivalents terms equivalent to t, which is equal to v of x. So therefore, this same trick. So if I interpret phi of t for x, so if I replace all the occurrences of x or free occurrences of x with t, then I get the same thing as I with v of phi. So I'm just replacing a usage of a variable with a term, and they both get sent to the same object. So these formulas will get the same truth value. I guess I'll have to continue on the next board. But now if I think about that substituted formula, the set of free variables of that, phi t for x, size of that set is n. So let me rewrite that. So I of v of, oh, whoops. I makes this formula true by the inductive hypothesis. So I of v of phi, which is equal to I of v of phi t for x, is equal to 1. And that concludes the proof, because I just showed that if you take any valuation, I of v of phi is true. And that's what I wanted to prove. The content of that is I just showed that when you interpret closed formulas, everything works out smoothly, as I proved in proposition 2. The extension to having variables is in effect because in effect you can just replace those variables with any representatives from the equivalence class of terms that variable is going to end up being interpreted as. Um, let me just sort of wrap up this sort of section and highlight what I just showed. Is this theorem, which we've been sort of building for a few lectures, which is if a set gamma is consistent, complete, and saturated, then gamma is satisfiable. And it's satisfiable by definition because I just exhibited an interpretation in which all of the formulas in that set are true. And the interpretation just interprets essentially closed terms as themselves up to equivalence with other closed terms. And truth in this interpretation is just elementhood is just the same thing as provability from an elementhood of this set of formulas. And so this is a weakened version of the completeness theorem because the completeness theorem is equivalent to this statement, but with uh, this part rubbed out, where if you have a consistent set, then you have an interpretation that makes it true. And so I've just shown it to be the case if you add these conditions of that set being complete and saturated. And so all I have to do to finish the completeness theorem is show that well, the way it's going to work is I'm going to show that if you take any consistent set of formulas, you can add some stuff to it such that it's complete and saturated, from which you'll get that extended set of formulas is satisfiable, from which it'll follow that the original set of formulas is satisfiable, and that'll be the completeness theorem. And we'll finish that next week. So thank you. Any questions?
Thanks, Kelly. That's cool.
No worries.